In this video, we're going to prove a corollary to the fundamental theorem of calculus part 1, and then we are going to prove the fundamental theorem of calculus part 2. So this corollary that we're going to take a look at, it says if, so we're going to let f be a continuous function on closed interval a to b, and g is continuous, or is differentiable on c to d, if the range of g over that interval is a subset of that closed interval a to b, for every single x in CD, we can define big F of x in this way. Right, so here we are replacing that upper limit of integration that we had in our last, in the fundamental theorem of calculus part 1. We're replacing that with g of x instead of just x itself. And when we do that, we find that f is differentiable on CD, on that closed interval. That big F is differentiable there. And its derivative, f prime of x, it is equal to f of g of x times g prime of x. And so we use, so our proof here, it's going to, I say it's a proof, that's very, way too generous. The idea here is just use the chain rule. So if you use the chain rule, then you will be able to work through that and get our particular derivative that we have there. Fundamental theorem of calculus part 2. So here, oh goodness. Here, if f is differentiable on a closed interval from a to b, and f prime is integrable on that closed interval from a to b, then the integral from, so here, let me change all this. So that was some bad LaTeX work. So the integral from a to b, the integral from a to b of f prime is equal to f of b minus f of a, right? So fundamental theorem of calculus part 2, this is the part that tells us here's how we can go through and evaluate definite integrals. And so now we have that. Let's prove this. So let P be this partition. And let that be any partition of that closed interval from a to b. By the mean value theorem on each subinterval. If we apply that mean value theorem on each subinterval, x sub I minus 1 to x sub I, we obtain points, let's call them t sub I, in the open interval so we obtain these points such that f of x sub I minus f of x sub I minus 1 is equal to f prime of t sub I times x sub I minus x sub I minus 1. So, we have f of b minus f of a is equal to the sum I equals 1 through n f of x sub I minus f of x sub I minus 1. So we have that, which each of those values there in that sum we can replace with these f primes at t sub i's. And this right here, this is really just delta x sub I, right? So this is that difference between those x sub i's. We know that little m sub I of f prime is less than or equal to f prime of t sub I. It's less than or equal to big M sub I of f prime for every single choice of I. So it follows that L of f prime comma p is less than or equal to f of b minus f of a, so that that lower sum should be less than or equal to the difference there, which should be less than or equal to the upper sum of f prime. And this holds for each partition. So, since this is true for each partition, we have L of f prime, the lower integral, should be less than or equal to f of b minus f of a, which is less than the upper integral of f prime. So we get that, and we know that f prime is integrable. And so since it's integrable, then these two values have to end up being the same. And that same value is the integral from a to b, f prime. Thus, that integral from a to b of f prime has to be equal to the difference between f of b and f of a. Nice. So that is the fundamental theorem of calculus, part 2, that we have used over and over in our early calculus days. But now we believe it to be true, and we can prove it to be true. All right. Thanks for watching. We'll talk to you guys later.